We've all looked up at the night sky and dreamed of visiting the stars. But there's a problem, right? The universe is just unbelievably vast. And we're stuck with this universal speed limit, the speed of light. So it's the ultimate sci-fi question. Can we ever break that limit? Can we ever travel faster than light? Let's dive in and see what the actual physics has to say. Now, when you think about FTL travel, two incredible ideas probably pop into your head. First, you've got the warp drive, this idea of stretching and squishing space itself. Then there's the wormhole, a kind of cosmic tunnel, a shortcut through the universe. But are these just cool concepts for movies, or could they actually be real? Does the language of Einstein's general relativity even allow for stuff like this? Okay, to even begin to answer that, we have to get on the same page as the physicists. We need to learn how to read their Mac. And I'm not talking about a map of stars and planets, but a map of space-time itself. Think about it like this. On Earth, we use latitude and longitude. But those are just labels, right? They tell you a location, but they don't tell you the real distance between, say, New York and London, especially since you have to travel over a curved surface. Well, space-time is the exact same idea, just, in 4 dimensions. The coordinates are just labels on a map. This brings up a huge question. If the coordinates are just arbitrary points on this crazy, curved, 4-dimensional map of our universe, how in the world do we figure out the actual distance or travel time between 2 points? We're going to need a special kind of ruler for this. And that special ruler is called the metric. You can think of it as the master rulebook for our cosmic map. The metric is the thing that tells you the true physical distance between any 2 points, and it automatically takes into account all the weird curving and warping of space-time that's caused by planets and stars and galaxies. It literally defines the geometry of our universe. And here it is, the heart of the whole thing. This equation defines something called the metric tensor. Now, don't get hung up on all the symbols. What's really important is that this little bundle of 10 functions has all the information about the shape of spacetime at any point. If you know the metric, you know the geometry, you know the rules of the road. So now we have our map and we have our rulebook. What are the rules for actually traveling on this map? Well, it turns out there's one really, really big one that changes everything. This is the light cone. And there's one of these at every single point in space and time. It is the absolute, non-negotiable speed limit of the universe. The edge of that cone is the path light takes. Anything with mass, you, me, a spaceship, has to travel on a path that stays inside the cone. Period. So here's the bottom line. Any possible trip you could ever take, any path through space-time, has to stay inside that light cone. Physicists call that a time-like path. Any destination that's outside your light cone is what's called space-like. And you simply cannot get there without breaking the speed of light, which the universe forbids. This is the law we're up against. But what if you could cheat? What if instead of trying to break the rule, instead of trying to go faster than light, you could just bend the very fabric of space-time that the rule is written on? This is where it gets really fun. This is the famous Alcubierre warp drive. Now look closely here. The ship inside the bubble is just puttering along. It's on a totally normal, time-like path. It never breaks the speed of light locally. But what the drive does is create a bubble of space-time around it. It squishes space in the front and expands it in the back. See how the light cones get tipped forward? The ship is basically surfing a wave of space-time, and that wave can go faster than light. And the payoff for something like this, it would be staggering. I mean, to quote directly from the source material, a warp drive would, quote, enable travel across the galaxy in times much less than the 100,000-year minimum. That's not just an improvement. That's a total game changer for humanity. Yeah, of course, in physics, there's pretty much always a but. And for the warp drive, it's a really, really big one. To make that space-time bubble, to bend space in that very specific way, the math demands something called negative energy density. You'd need some kind of exotic matter that has essentially anti-gravity. It would push space apart instead of pulling it together. The problem? We have never, ever seen anything like this. It's completely theoretical. Okay, so if the warp drive is on hold, let's turn to our other great sci-fi hope, the wormhole. This picture shows it perfectly. A wormhole isn't about moving space around you. It's about punching a tunnel through space. It's a shortcut, a throat that could connect 2 parts of the galaxy that are millions of light years apart. And, wouldn't you know it, we slam into the exact same wall. To keep that wormhole's throat from instantly collapsing in on itself, the physics says you need to prop it open with that exact same hypothetical exotic matter. All the stuff we know, stars, planets, you, me, light itself, it all has positive energy. The one ingredient we need to make it work is the one ingredient we have no idea how to find. So where does all this leave us? We've got two absolutely brilliant ideas, both of them totally valid according to the mathematics of general relativity, but both of them require a physical ingredient that seems to be pure fantasy. So what's the final verdict here? Well, the source text itself doesn't really pull any punches. It concludes that without some source of this exotic matter, and I quote, "The future domain of applications for wormhole geometry is probably entirely fictional." That's a pretty sober assessment, but it's based on what we know about physics right now. Does that mean we should just give up? Is the dream of faster-than-light travel just a fun story, something that's always going to be stuck on the pages of sci-fi novels? And this is the really wild thought I want to leave you with. What's so amazing is that the language of general relativity is real. The math that describes a warp drive or a wormhole is perfectly solid. The geometry is possible. The only piece of the puzzle we're missing is the physics, a real physical substance to actually build it. So maybe the question isn't, can it be done, but more like, is there something fundamental about how the universe works that we just haven't discovered yet?